Yes, any questions before we continue? You see, this is let's just assume, for simplicity, psi I to be orthogonal to each other. Then the eigenvalue is omega I. Omega I is the probability that my particle will be in the state psi I. Psi I is the eigenvector. So if you diagonalize this row, if you pick up a random particle in your ensemble, it can be in one of your eigenvectors, and the probability that your particle will be within that eigenvector, in the state described by that eigenvector, is the corresponding eigenvalue. Yes? In that sense, omega I are analogous to classical probabilities. So kind of here we are mixing the classical concept, the density matrix just combines the classical probability concepts and quantum mechanical concepts. And when we were also talking about the averages, this average contains both the quantum average over the states and also the classical average over the ensemble. So now we have both of those probability concepts, both the quantum probability concepts and also the classical probability concepts. Yes. Of course, in that case, you still can diagonalize the density. They don't have to be diagonal. They can still be orthogonalized. The row, it's a Hermitian matrix. It can be diagonalized. And the eigenvalues will still correspond to the probabilities that if you pick a random particle, it will, the probability that that particle will be in a state with the corresponding eigenvector. Of course, if psi i's are not orthogonal to each other, then the eigenvectors will not be psi i's. They will be different vectors. Well, you see, the evolution of the density operator is still determined by the Hamiltonian. So if you know the initial value of your density matrix, then you can determine how it evolves in time. Well, you see, the probabilities do not, but the kets are evolving, unless they are stationary states. Unless you have an ensemble of particles that are all created in stationary states, then rho will be evolving in time. You see, this omega I, psi I, rho of t will be just this one. If psi I of t are stationary states, then psi I of t, we already know that this is equal to e to the power minus I over h bar, ei times t times psi I. So rho of t is equal to rho of omega I e to the power minus I over h bar ei of t psi I e to power I over h bar, ei of t. They will cancel. So what remains is rho at t equal to 0. But then you can ask the question, let's say, whatever the density matrix is, I can always write it in an energy basis. Then what? Well, let's see. Rho of t will be equal to omega I, psi I of t, psi I of t. Let's assume are not stationary states. Well, I can write the psi I of t in terms of the psi I, let's say, in terms of stationary states, let's call them ei, with coefficients given by ei psi I. Psi I of t will be, well, okay, now let me just change the notation. Let me call these j, I'm summing over j. The time dependence will be given by e to power minus I over h bar ej of t, ej psi I. So let me write what is rho of t. This is equal to sum over I, omega I, sum over j, e to power minus I over h bar, ej of t, ej psi I, times sum over k, e to power I over h bar, ek of t, ek psi I, ek. You see, in this case, since j and k can be different, they don't cancel. So rho is time dependent. Or you can say, well, what if I first diagonalize and look at its time evolution? Well, easy. Let's look at that one. Rho at t equal to 0, we said this is equal to omega I, psi I, which can be written as ijk omega I, let's say ej psi I, ek psi I, ek. Sum over j and k, sum over I, omega I, ej psi I, ek, ej, ek. It's not diagonal. Well, let me just call this thing rho jk. Sum over jk, rho jk, ej, ek. As I said, it's not diagonal, since I didn't create it as an ensemble of stationary states. If I look at the time evolution, sum over jk, rho jk, the time evolution of ej, it just acquires a phase, e to power minus I over h bar, ej times t, ej, ek, e to power I over h bar, ek of t. Rho jk, e to power minus I omega jk of t, ej, ek, where I define this omega jk is equal to ej minus ek divided by h bar. If it's not diagonal in the energy basis, If the density of states, then it will evolve in time. It will have a time dependence. You are right, omega i's do not change, but the states are changing. And hence the density matrix will change. And we can also write the density matrix for a continuum of states, if you like. You see, for example, rho, we can write it if we don't have a discrete states, but a continuum of states like the position. Then this will be dx. Let's say, no. Omega I, psi I, we can basically create it in one of the finite number of kets. But we can look at its matrix elements, for example, x prime, which is x rho x prime. This will be equal to sum over I, omega I, psi I of x, psi I star of x prime. This is the matrix elements of the density matrix in the position basis. Then rho in this, since these are the matrix elements, we can write it as dx prime, rho of x prime, x prime. This is my density matrix in the position space. Well, it's interesting to look at what the diagonal elements are. Rho xx. This will be sum over I, omega I, psi I of x squared. Well, the psi I of x absolute squared is nothing but the probability density. In fact, this is why we call that the density matrix. In the position basis, at least, it gives us the probability density. Also, in the momentum basis, the diagonal elements will be the momentum probability densities. Other questions? Well, let's look at then, change of subject. We had defined these generators of rotation, but we didn't really study them yet. Well, what are their eigenvalues, eigenvectors, etc.? Well, we looked at only the particular case of the spin that we kind of know, but we can just make a general treatment of them also. And the only thing we will need is that the commutator of ji with jj is I times epsilon I jk. This is the only thing we need, and this is what we had derived when we were studying the rotations. This is nothing but the commutation relation for rotations in three-dimensional space. So the corresponding operators in the Hilbert space should also satisfy the same commutation relations. Now let's look at, our strategy will be just like the way we solved the harmonic oscillator. So if you remember the harmonic oscillator, we wrote the Hamiltonian, and then we defined two operators, the annihilation and creation operators. In that case, we call them annihilation and creation operators, which just change the eigenvalue of the Hamiltonian by plus or minus 1. So we will basically do a similar thing over here. Now first, since the different components of J, they do not commute, we cannot diagonalize them at the same time. We can at most diagonalize one of them. You can just choose whichever one you want to diagonalize. And conventionally, we choose JZ. So we diagonalize JZ. Now let's look at this one. Let's just show this also. J squared, which we define as Jx squared plus Jy squared plus Jz squared. Let's also calculate its commutator with one of these Ji's. So if I rotate my system, how does the magnitude of the angular momentum of a system change? Under rotations? It doesn't change. The magnitudes do not change under rotations. So this should be 0. You see, if you remember how we studied how an operator rotates under rotation, you see, let's look at any operator. We looked at how the Jx rotates under rotation before. Any operator, when you rotate it, this is nothing but, let's say, alpha e to power I over h bar j dot n theta, O e to power minus I over h bar j dot n theta, alpha. This is the rotated matrix element. If something doesn't change under rotation, this rotated matrix element should be alpha O alpha. But if this is to be satisfied, O should be rotated, should commute with j dot n. So that's just one way of arguing that this j squared commutator with ji should be 0. But we can calculate it explicitly. Let me write it in this form. This is jz, jj, jj, ji. The first one is j squared, which I can write as jj commutator of jj, ji plus jj, ji commutator multiplied with jj, where I use the property that the commutator of the product of A and B with C is just A times B and C commutator plus A and C commutator multiplied by B. This is what I use. I know what each one of these commutators are. This is jj, epsilon. Now this is I h bar, epsilon j I k j k, plus I know what the other commutator also is. It is I h bar, epsilon j I k j k j j. So this is equal to I h bar, epsilon j I k j j j k plus j k j j. Can you see that this is 0? Well, you see, in general, you can see that this is actually 0 by just looking at, you see, epsilon j I k is anti-symmetric if you exchange j and k. Whereas that quantity in parentheses is symmetric. It doesn't change sign if you change j and k. Whenever you multiply a symmetric tensor with an anti-symmetric tensor, you get always 0. To see that that is actually the case, let me just write it in this form. I h bar. You see, I'm summing over j and k. So they are just what we call dummy indices. I can just change their name whichever way I like. So instead of j, I can write k. Instead of k, I can write j. I'm just changing their name. Now, in the Levi-Civita, I can just exchange. Now I'm not changing the name. I'm changing the place of j and k. But if I change the place of j and k, I get a minus sign. Now compare these two lines. The term in the parentheses in the first line and the last line, they are the same. The epsilons, Levi-Civita tensors, they are the same. The indices are in the same order. I, H bar, they are the same. So that the first line in the arrow is minus itself. It just tells me that it should be 0. So basically, I know that j squared and ji, this is 0 for all I. You can just put x, y, or z, they all commute. So since they commute, I can diagonalize them together. I can choose an I can diagonalize that ji and j squared at the same time. But I cannot diagonalize, let's say, jx, jy, and j squared, because jx and jy, they do not commute. So that's the problem. Not the problem, but that just tells me that I can diagonalize at most 2 of these operators. I can diagonalize j squared and one of jx, jy, jz. And conventionally, we choose jz. So these are the 2 operators that we can diagonalize. They can have, there are eigenvectors which are eigenvectors of both of these operators. Well, I don't yet know what the eigenvalues are, but let me just call those states, those kets A and B. J squared acting on this ket just gives me A times A and B. Jz acting on this ket just gives me B times AB. These are the eigenkets with the eigenvalues A and B. Now my task will be what are the possible values of this A and B. That is what we will try to determine. Now let me look at one particular commutator. Now, I know that Jx and Jz commutator will be minus I H bar Jy, and Jy, Jz, the commutator will be I H bar Jx. These are the general commutation relations. Now let me look at the commutator of Jx plus I Jy. Now if you remember the harmonic oscillator analogy, there we had defined these operators A and A dagger. They were just x plus p, I, p, x minus I, p with certain coefficients. Now in this case, let me do a similar construct. Let me just look at the superposition of Jx and Jy. Jx plus I, Jy, let me calculate its commutator with Jz. This will be equal to, well, Jx commutator with Jz is minus I H bar Jy plus I. Jy commutator with Jz is I H bar Jx. So this will be equal to minus H bar Jx plus I Jy. So you see, I have one operator. I'm calculating its commutator with Jz. I obtain the same operator with a proportionality constant. Well, that operator I will call J plus. And so J plus commutator with Jz, this is equal to minus H bar J plus. Now let's see what this implies. Let me act with J plus Jz. This is an operator on this ket AB. Now on one hand I have J plus Jz acting on AB minus Jz, J plus acting on AB. This is equal to minus H bar J plus AB. Well, by definition, I know that this is nothing but B times AB. So Jz, J plus AB is nothing but B plus H bar J plus AB. You see, if AB is an eigenvector of Jz, then we know that J plus AB is also an eigenvector of Jz with an eigenvalue increased by H bar. So J plus AB will be some coefficient which might depend on A and B, we don't know, we will calculate it eventually, times A, B plus H bar. Now I can do a similar thing with J minus. Jx minus I Jy, commutator with Jz. This will be equal to Jx and Jz commutator gives me minus I H bar Jy, minus I, the commutator of Jy and Jz is I H bar Jx. This is equal to H bar Jx minus I Jy. So I will define this as J minus. This is Jx minus I Jy. And so J minus Jz is equal to H bar J minus. Well, it's almost actual. It's similar to this one, but it's just this minus sign now is plus. So that minus sign basically determines the sign over here. So you can just do the same treatment, and what you will obtain is Jz acting on J minus AB. This is equal to B minus H bar AB, J minus AB. So again, this also tells me that J minus acting on B, AB, well, up to a proportion normalization constant, it is A, B minus H bar. So in a sense, this J plus and J minus, they are similar to our annihilation, creation and annihilation operators. Of course, they change the value of Jz, the eigenvalue of Jz. In the case of the harmonic oscillator, they were changing the eigenvalue of the Hamiltonian. Well, since this is not the Hamiltonian, these are usually called the raising and lowering operators. J plus is called the raising operator. And J minus is called the lowering operator. They raise and lower the eigenvalue of Jz. Now, of course, are there any limits on this raising and lowering operator? So what the eigenvalues of Jz, are they limited from the above or from the below? So let's see. Now, first of all, we already know that we had defined J plus minus to be Jx plus or minus I Jy. Now, let's look at J squared. We know that J squared is Jx squared plus Jy squared plus Jz squared. Well, we can write Jx and Jy in terms of this J plus and J minus. Jx is J plus Jy, J minus over 2, and Jy is J plus minus J minus over 2i. In a sense, Jx is the real part and J minus is the imaginary part. And J plus dagger is J minus. So you can just think of these as J plus the imaginary part, the complex conjugate of J plus divided by 2 gives me the real part. J plus minus the conjugate of J plus divided by 2i gives me the imaginary part, in a sense. So let's put them over here. This is J plus J minus over 2 squared plus J plus minus J minus over 2i squared plus Jz squared. This is equal to 1 over 2, that's 1 over 4 j plus squared plus j minus squared plus j minus plus j minus j plus. This is the first one. The second one, minus 1 over 4 j plus squared plus j minus squared minus j plus j minus plus j minus j plus jz squared. This is my j squared. Well, j plus squares, they cancel. J minus squares, they cancel. This minus makes this plus and this plus. So what remains over here, this j plus j minus, here I have another j plus j minus, that's 2. J minus j plus, here I have another j minus j plus, that makes 2. So j squared is 1 over 2, j plus j minus, plus j minus j plus jz squared. Well, it would be nice if I just exchange the place of j plus and j minus. So then I could just add this j plus j minus and j minus j plus. That would just give me 2. So it would look simpler. Let's see how I can commute them. Let's calculate the commutator of j plus and j minus. This is equal to jx plus ijy, jx minus ijy. This is equal to jx, commutator of jx with minus ijy, plus the commutator of ijy with jx, because basically jx commute with jx, jy commute with jy. This is equal to minus I times I h bar jz, this is the first term, plus I times that commutator is minus I h bar jz. So we get j plus j minus is equal to 2h bar jz. So what does this tell me? J plus j minus minus j minus j plus is equal to 2h bar jz. So instead of, if you like, j plus j minus, I can just change their place. That becomes j minus j plus. But this time there is plus 2h bar jz. Okay, let's go back. This is equal to 1 over 2 j minus j plus 2h bar jz plus j minus j plus jz squared, or j squared is equal to j minus j plus h bar j minus h bar jz, sorry, this is not j minus, this is jz, plus jz squared. No, that's correct. Let's look at this one. AB, J squared, AB. On one hand, this is A, should be equal to, well, this, let's say AB, J plus dagger, J plus AB, plus JZ squared will be just B squared, plus H bar times A. No, H bar times B, sorry. You see, this is fixed. If you act with J plus and J minus, you can change B without changing A. It's just some number fixed. This is always positive, because you have an operator, multiply with its dagger, take its average, that's always positive. This is always positive. But B can be, if B can be as negative as you like, you will start having problems. Or, you see, this is B, no, these are, let's see. No, I cannot really say that. Because B squared plus H bar B, it is bounded from below. So this doesn't really tell me that B should have a bound. But what can I say? J squared, which is Jx squared plus Jy squared. This is all plus Jz squared. This is always larger than Jz squared. The average. So if you take the average indicate AB, this should be larger or equal to the average of AB Jz squared AB. This should be always larger than or equal to B squared. So A should be always larger than or equal to B squared. This is basically what we have over here. These are always positive, but this is always larger than B squared, because this is positive. It can be positive or negative. Well, if it is negative, okay, from here it's not so easy to see, but from here Jx squared average will always be positive, Jy squared average will always be positive, so the average of J squared should always be larger than the average of Jz squared. So that tells me that A should be larger than B squared all the time. But this tells me that there should be an upper bound for B. And for that upper bound, let's say B max, if you try to increase it, this should be 0. If it's not 0, it will be an eigenvalue it will be an eigenket with an eigenvalue larger than B max. Now I can look at this one. Now if I act j squared on this ket, well, on one hand I know that that is equal to a times my ket. On the other hand, j squared is j minus j plus h bar jz plus jz squared acting on a b max. Well, this just gives me 0. I cannot increase b any further. And what I am left with is h times b max plus b max squared. Well, this tells me that the eigenvalue of j squared can be written as b max times b max plus h bar. Of course, conventionally, we don't use a and b to denote our eigenvalues. Conventionally, b is h bar times m, and a b max is j times h bar. So a is h bar squared j plus 1. So my kets are, instead of a, b, I just use j and m. So up to now what we had shown is, well, there are MJs. I don't really yet know what these MJs are yet. But I know that JZ acting on this state JM just gives me H bar M, JM. J squared acting on this ket JM gives me H bar squared J plus 1, JM. And J plus acting on JJ, this is 0. Okay, so let's go back to this equation. We said that B has an upper limit, but that equation also tells me that B has a lower limit. Because minus B squared is equal to B squared. So if B has an upper limit, minus B should also have an upper limit. That means B has a lower limit. Do you agree? So B, A is larger than B squared also implies that B has a lower limit. B min, such that J minus acting on this well, let's just go back. B has a lower limit, B min, which we can write as H bar times M, minimum value of M. J minus acting on this state J, M min, this should be 0. Let's go back to this relation, but this time I want to change the position of J plus and J minus. So this tells me that J minus J plus is equal to J plus J minus 2H bar JZ. So J squared, I can also write it as J plus J minus H bar JZ plus JZ squared. I can act this operator on J M min. On one hand, I know that it's the eigenvalue of j squared is given by j. This is h bar squared j plus 1. Well, j minus, this is equal to j plus j minus h bar jz plus jz squared j m min. Well, j minus acting on this ket gives 0. What I am left with is h bar squared m min times m min minus 1. So it's just the first term is jz squared. This is this term. This minus 1 is this one. So this tells me that j times j plus 1 is equal to m min times m min minus 1. If you solve this equation, you will see that m min, the minimum value of m, is minus j, which is minus the maximum value of j, m. So we have all these j, m. M should be between m min, m max, and m should be between, let's say, j and minus j. But you see, if I start from jj, I can lower it to j minus 1, then j minus 2. I can just keep lowering it one by one. And since m has a lower limit, I should eventually reach j m min. Eventually. Well, but this tells me that I should reach m min is minus j. So if I start from j by lowering it by 1, I should eventually come to minus j. But this tells me that, well, how many steps? 2j plus 1 steps. So 2j plus 1 has to be an integer. So this just limits the possible values of j. I mean, up to this point, we didn't really know what are the limits. We know that the maximum value of m was j, the minimum value was minus j. But now, since we should just lower m by 1, and if we are to stop, well, eventually we should reach the minimum value. And so in a finite number of steps, we reach the minimum value. The number of steps is an integer. So 2j plus 1 has to be an integer. Well, this doesn't tell me that j has to be an integer. J doesn't have to be an integer, but it is either integer or half integer. So this basically completes our discussion on the possible eigenvalues and the eigenvectors. Well, still we need to discuss how does the j plus j minus act. We know that they change the eigenvalue, but how do they change the normalization, etc. Well, but that we will do on Monday. Any questions on this one? Okay, so see you on Monday.